Okay, I've got a question here. He doesn't know how to use coefficient of friction. Let me show you how to use coefficient of friction, okay? All right, go. Then paper. Who's that? Who else is that? Why is there another person joining? Huh? Who's that? Glendon, don't be idiot. Wondering who joined. Sorry, Ian, I realized that you were not looking at the share screen. Now, can you see me? Yeah, sorry. Okay, so you can see me. You can take down the notes. So I got a question here, right? Asking about how to use coefficient of friction. Let me just give you a quick example. I have a box on the slope where the box is 80 kilograms. Okay, just give you a random one, right? Box on the slope 80 kilograms. The angle of incline is 30 degrees, and I tell you that the coefficient mu is 0.6. Okay, and I ask you, tell me what's going to happen to this box. Tell me what's going to happen to this box. Just like that. So you have to do everything lah. You basically have to do everything. It's like I give you a box sitting on a slope, right? 30 degrees, coefficient of friction is 0.6, right? And then, oh wait, hold on. Yeah. Okay, lah. That's to be specific, 0.58. Okay, 0.58. What's gonna happen to this box? Right. So what are the things you need to find? You need to find the force down the slope, right? Okay. Now you see, right? I can go through the whole process with you again, but it will take very long. It will be like something like this. I give you the N, I give you the mg, right? And then you know that there's friction because I tell you there's a coefficient, so there must be friction, right? Okay. Now the understanding is that the friction is equal to what? Mu n. Oh, friction is equal to mu n. You understand this? Yeah, friction is equal to mu n. That's how you use the coefficient, right? But what is n? Do you have n? Don't have. Then what can you do to find n? What can you do to find n? Resolve what? Resolve the mg. Okay. So you resolve it like that. Then what is this component here called? mg cosine 30, right? Then the other one, mg sine 30 degrees, okay? So your job is to go and find out which one is bigger, mg sine 30 or f equals to mu n. Which one is bigger? You get it? Don't know. That's your job to find. Your job is to find whether it will be stationary or not. Right? So work out the values. Work out the values. Work it out now. Where's the calculator? Bring it out. Work it out. If you think physics is hard, wait until you do math, lah. All right. These are already very simplified, like calculation stuff. That's why people like to do physics over bio, right? Now, a few simple rules for you to remember. Once you remember those rules, you apply those rules, you get the answer all the time. Huh? I'm sorry, what? No, I'm asking you to find whether the friction is bigger or this one is bigger. I didn't ask you to find mg cosine 30. I asked you to find the friction. So how much is the friction? Huh? It's the same as this one, right? It balances, right? Take down the notes. Draw the forces. Your forces are not drawn properly. Both like you at least you drew it properly. Your forces are not drawn properly at all. Where's your forces? You should be drawing on the box itself, right? On the slope. Why do you draw it on the slope there, over there, right? And use pencil if you have to, right? If you're not sure, please use pencil and draw it. Which one is bigger? How much is this frictional force here? 0. Huh? The friction is only so little. 0.58 times. What's n? Hey, hello. Hey, no. Don't go and cancel it. Nobody asked you to cancel the stuff. How much is the friction? 394.2 newtons. And how much is the mg sine theta? 392.4. Wow, almost only, right? Okay. Is he correct? Confirm, huh? So basically, this box is going to be stationary. Yeah, this box is going to be stationary. Right? Because it can't overcome the static friction. Just only, actually. I gave you the numbers, it's like just only. And so if I were to give you this coefficient of static, this coefficient of friction, right, you must understand that this is the coefficient of static friction. So the idea is it is not able to overcome this static friction yet. But let me ask you this, okay? If let's say just nice are the same, let's say 393 on both sides, and I give this box a slight push, right, an extra push to get it to start moving, will it continue moving after you let go? Why? Excellent, right? Kinetic friction is lesser than static friction. So if let's say just nice 393, it doesn't move. If you give it a slight push, after that it starts moving, it will continue to move because it will change to kinetic friction. Do you hear that? Right? It will change to kinetic friction. Are we okay? And this is how this thing works. Okay, yeah? Okay, good. That's what coefficient of friction is used to do, right? To help you calculate the friction. Ian, have you copied down everything? Okay, yeah. All right. I want to continue with where I left off, but I cannot remember where I left off. So where did I leave off? Did I do this one? Yeah, the explosions, not yet. Okay, I'm gonna do it now. So recap, recap. How many types of collisions do you have? Three types, You have three types of collisions: elastic, inelastic, and perfectly inelastic. Or rather, nowadays I like to change it to completely inelastic. Right, completely inelastic. Did I give you an example for bullet and the box? Did I do an example for bullet and a box? No, I didn't do an example of bullet and box. Okay, so I'm gonna do that now. Okay. All right, but before I do that, I'm gonna ask you this. So what's the difference between elastic, inelastic, and completely inelastic? What are the differences between these three? So elastic, what's the definition of elastic interactions? Total K is conserved before and after the interaction, right? K is conserved before and after. How about inelastic? How about inelastic? Yeah, K is not conserved, right? Total kinetic energy is not conserved, right? Is as straightforward as that. So elastic is conserved, inelastic is not conserved. How about completely inelastic? Completely inelastic is? Yeah, right? They're stuck together after they collide, right? Okay. Have you gotten this memorized? Because here's the thing, I cannot do this again later, no? There's no time. Right? You have to get this right here, right now. You have to memorize this so that next week if I ask you the same question, you have to give me the same answer. Right? Elastic is what? K. Okay, if I ask you to define elastic, you're supposed to only say K is conserved. You cannot say momentum is conserved. Why can't you say momentum is conserved? Because momentum is conserved for all situations, right? So you cannot use it as a definition, right? So elastic collisions, right? Ke is conserved before and after. Inelastic, K is not conserved. Completely inelastic means that it is an inelastic collision, meaning that K is not conserved, and they also move together at the same speed after the collision, right? It is an inelastic collision. Are we okay on this? Can. Okay. So I'm going to go through some examples now, right? Let's go through some examples. This is 8 meters per second. This is 2 meters per second. Okay. And then what happens is that this one will roll forward at 6 meters per second, and this one will go backwards at 4 meters per second. Can you tell me if this is an elastic collision or not? right? So I draw the collision in the middle. So this before, this after. Is this a elastic collision or not? He said yes. You think so? You? Huh? Wait. Yes or no? It's not. Yes, yes. Yes. You? Why yes? Huh? What? Wait, I'm asking, is this elastic or inelastic? Okay, what is it? It's inelastic. You say that's inelastic. You were saying that. What were you saying? You said elastic, so I have another answer for elastic. One inelastic, one elastic. You were saying that it's elastic. Okay. There's no mass, huh? I didn't tell you the mass, you know. All you have to do is just check the velocities, right? Okay, huh? So, hang on, maybe my handwriting, I don't know. What's the relative speed of approach here? 10. Right? What will be the relative speed of separation here? So actually, I made a mistake, guys. Do you see that I made a mistake?
Oh yeah.
Do you realize that this is impossible? How can you collide already, then after that go on and collide again? Right or not? Okay, so please look at the things, right? Look at the values. Okay, hang on. Let's change this then. Let's say we make this let's say 16 meters per second. So just now the example, right, was just to show you that that's completely wrong because it can't collide and then collide again. Because if this is 6 and 4, it's going to collide again. So it collides one time and then that's it, right? It will separate. So now what happens if the numbers are like that? This will be elastic collision, right? There will be elastic collision. Okay, so this one will be elastic, right? Just simply looking at the velocities. Okay, which one is more massive? Which object is more massive? Right, I'm going to call this A, I'm going to call this B. Which one is more massive? A. A is more massive, right? Now I ask you to prove it. How do you prove that A is more massive? Find what momentum? Find the change in momentum. Okay, you can say MA times 8 plus MB times minus 2 equals to MA times 6 plus MB times 16. Agree or not? The working? Hey, copy this down, come on. Right, fast one. So this chapter, this part of this chapter in particular, you have to do a lot of practice questions. Right, show me that MA, what's the ratio of MA to MB? Mass of A over the mass of B. What? 1:9? Good. 9 over 1. Or 1 over 9. Wait, you all see first, huh? MA to MB is 1:9. Okay, A is more massive, right? So the mass of A is 9 times the mass of B. So I would say 9 over 1 is correct. Yeah. Right? You mean you cross multiply, it's MA equals to 9 times of MB, lah, right? Not right? So that makes sense, right? Okay, so 9 times. Okay, there we go. Okay, can I give you half a question? I'm gonna give you half a question now. This is also elastic. This is also based on elastic collision. So I'm gonna give you half a question. Um, let's say we use the same masses. No, wait, let's not use the same mass. Let's use a different set of mass. Let's say this is 10 kg, and this is 2 kg, for example. Okay, right? Let's say this one is moving at 8 meters per second, and this one is moving at 1 meters per second. Right? Okay, your job is to find both their final velocities. Yeah, your job is to find both their final velocity. So we don't know what's VA and we don't know what's VB. Your job is to find VA and VB. Okay? All right. Now, why is this more difficult? Because now I have two unknowns. I don't know what's VA, I don't know what's VB, right? Okay, I have two unknowns. So then now I'm asking you to solve it completely, which means that you definitely have to find VA and VB. I'm not asking you for a ratio of VA to VB. You have to find VA and VB. Okay? But let me just guide you with this first, all right? Please listen to the guidance, all right? Let me remind you one thing. So since you have two unknowns, how many equations do you need to use? You need to use two equations, right? For elastic collisions, EC, elastic collisions, do you have two equations? Do you have two equations? What are the two equations that you can use? The momentum equation, right? The conservation momentum equation, and the no. What's the other? I just said momentum equation. Huh? No. Look at the notes, please. Look through the notes. If you're not sure, look through the notes. Right? What's the other equation that you can use? So u1 minus u2 equals to v2 minus v1, right? That's the other equation, correct or not? Okay. So I'm just going to write that down. So you got your MAUA plus MBUB equals to MAVA plus MBVB followed by UA minus UB equals to VB minus VA, both of them modeled, right? That is okay. Ian, okay there? Okay, quick question now. I must tell you this, okay? I must remind you this. Right? I said that I'm giving you half a question because I'm guiding you up to this point. Just remember this. Always remember to use the momentum equation first. You come up with the expression of the momentum equation first. Then you go and then you use the second one. This is number one, this is number two, right? Then you sub number two into number one, not the other way around. This is a very specific procedure, right? For problem solving. It's just that if students do it the other way around, most of the time they get it wrong, right? So you always express one first and then you sub two into one. Never sub one into two. Yeah, yeah, sorry. Use this one first, then this one, right? Okay, so we express equation one first. Can I get the expression for equation one? When I no, as in I do number one first. Number one is basically as in I simplify number one first. This is 10 plus, sorry, 10 minus 16 equals to 10 VA plus 2 VB. Okay, right? Then for number two, so what you want to do is maybe you want to make VA the subject first. Let's say you make VA the subject. What's the answer for VA? Let's say you make it the subject first. You will get minus 6 minus 2 VB, correct? Minus 6 minus 2 VB, yeah? Right. You will sub this into the other equation. You do not do it the other way around. You don't work this one first, then you sub it into number one, right? The reason is this. The first one is a vector equation. So the first one will tell you the direction very clearly. The second one is a scalar equation, right? So the second one, right, if you sub a scalar into a vector, you will lose the direction. So if you sub a vector into a scalar equation, you will retain the direction. Okay, what's UA minus UB? How much is UA minus UB for equation 2? What's that? 9, right? Okay, 9, so it's mod, so it's just 9, right? Full on, just positive 9. Then you got VB minus VA. I'm going to sub in VA now. Am I right? Okay, then you can find VB already. What is VB? Never mind, I just do the whole question with you lah. I'm doing the whole question with you already. So how much is VB, guys? So I'm using equation 1, MA times UA, 10 times 1. So the MAUA, this one here is 10. Yeah. The back part, 10. Oh, sorry, I forgot the 10. Yeah. Sorry, I forgot about 10. Sorry. So divide by 10, right? This thing here also divide by 10. Sorry about it. Yeah, forgot about the 10. So there's a divide by 10 here. Yeah, then you have to make sure you have to solve for VB. Yeah. What about it? You got this fixed? Hmm? Oh, just nice on the dot 7. Oh, okay, 7 meters per second. Do you get it as a positive value or negative value? Positive value? Okay, good. So it is likely that VB will be bouncing off at 7 meters per second to the right, because we're taking positive as right? So now you have to check for VA, right? You have to check for VA, right? If VA is a negative value, then yeah, it goes backwards. If VA is a positive value, then it actually goes forward. So the arrow I drawn is wrong, right? But how much? Like, what's the final value for VA? What? Oh, just nice minus 2 also. Oh, okay. Right. So yeah, okay. So that means VA does go backwards at minus 2. Right, 2 meters per second. Okay. And this is how it's done. Now again I repeat, the only reason why you can have two equations, right, is because this is the elastic collision, right? Because I already declared to you that it's elastic. So if it's elastic, you can use these two. So that means that it's right for me to give you two unknowns. You can go and calculate two unknowns, right? The trick here is, if this is inelastic, You cannot use both equations. You only got the first one. Okay? And then one last time again, for elastic collision, always work the first one, the momentum equation first, then you sub it into this one, not the other way around. Okay? Very important. Every time you see elastic equations, right, elastic calculations, always work this one first, then you sub it into the second one. Don't do it the other way around. Right, I've done many questions before where if students do the second one first and try to sub it into the first one, right, they get it wrong. Right, because the second one is a scalar equation, not a vector. Okay, that's for elastic. Right, can I do one more? I'll do one more. Quick one, come. I got a wooden block hanging on a string. I got a bullet flying in. Right, the wooden block is 10 kilograms. Right, the bullet is 10 grams. Okay, it's a 10-gram bullet and a 10-kilogram wooden block. I tell you that when the bullet block the bullet enters, right, and gets embedded into the wooden block like this, right, it gets embedded in, right. The question is this: what is the speed after impact, right? Given that the bullet is moving at 300 meters per second. No, that's a bit, yeah, 300 meters per second. That's the speed of sound, right? Okay, that's fine. Yeah, right. Let's say it's moving at 300 meters per second. Okay, right. What is the final speed after impact? That means you have to understand that the bullet must impact the wooden block first, then the two of them will move together. So what's the final speed after impact? Okay, number one, let me ask you this, guys. Let me ask you this. Does the bullet have KE? Does the bullet have KE? It has KE, yeah? Can I assume, next time your diagram, please draw a bit bigger, right? This is non-committal drawing, all right? Draw a bit bigger, okay? The bullet has KE. Can I assume that the KE of this bullet is fully converted into the total KE of the system, then they move together? Can I assume that this initial KE equals to the final KE of both objects moving? Absolutely not. Why can't I do that? Why can't I assume that the bullet of the KE is converted into the KE of the entire system here? Not good enough. Why can't I assume that the KE of the bullet is the KE of the entire system after impact? I know it will be I mean, that's just declaring that it will not be conserved. I'm asking you, why can't I conserve it? Why is it not conserved? Why is it lost as heat and sound? You're not wrong, but like, why is it lost as heat and sound? What's the rationale behind it? Right? I give you a clue. I repeat this statement one more time. The bullet after impact is embedded into the wooden block. That's your clue. It is a completely inelastic collision, right? Because of how I described it, right? I said that the bullet is embedded into the wooden block, right? So if it's embedded into the wooden block, it's a completely inelastic collision. And what is the clue that you have to derive here? Why is Ke not conserved? Because it's an inelastic collision, right? It's a form of inelastic collision. Ke is not conserved, which means that the Ke of the bullet will not be the Ke of the bullet and block system after impact. It will not be conserved. Some Ke will be lost. Understand this? So therefore, your job now is to calculate what is the speed after impact and what equation will you use? Yeah, which one? Which one? Read out the whole thing. Wrong. That's not the equation I taught you. Yes. MA plus MB V3, right? So we are looking for this V, right? So we just put it as V, sorry. Right, I can just keep it as V. So I want to just make sure that you remember that both objects are combined after the collision, right? They move off together with a certain V. Right, so please calculate the final velocity after impact. Have you found the final velocity? 0.299 meters per second. Ian, did you get the value? 0.299 meters per second, everyone? Okay. I want you to calculate the KE lost. How much KE was lost in this process? Right, since you know it's a completely inelastic, KE is lost. Right, so how much KE is lost in this process? Of the whole system, yes. Everyone? Yeah, 449.5, right. The change in KU is basically 450 minus 0.45 joules actually, right? 450 minus this answer. Yeah, so it's 449.5, maybe 55 joules now, right? 55 joules. I just okay. So just to show you that this is a loss in KE. This is the amount of KE that's lost. Everyone know how to do this kind of questions already? And right. On top of this, they're gonna tell you this, okay? Right? They're gonna tell you that this thing here will swing upwards. Right? It will swing upwards. After impact, it will swing upwards. Then they will ask you, so what's the maximum height they will swing up to? Right? So the final K is actually very small, right? So based on the numbers I've used, the final K is very, very small. It's 0.45 joules only, right? Okay, so 0.45 joules equals to mgh, right? And this m is the combined mass, so it's 10.01 kg, right? The combined mass is 10.01 kg, so the h is not going to be a lot, right? So your job is to find out what's the height that it swings up to. Yeah. So 0.45 divided by mass of 10.01 divided by 9.1. So the height is just going to be, well, even though I say it's not a lot, it's, you know, yeah, 0.44 meters. All physics equation uses SI, right? So it still goes up to about 40 cm, right? So it still swings upwards about 40 cm. Okay? I hope I didn't get this wrong. 0.45 divided by 10 kg times 9.1. Yeah. Hey, no. So, made a mistake. So it's 4.58 times 10 to the power minus 3 meters. Right, 4.59 times 10 to the power minus 3 meters. Right, you all got that? So yeah, it's a very small height. I don't know why I got the wrong mistake. Wrong values here. So it swings up only a little bit, like what was this? 5 mm? 5 mm? This 5 mm. Yeah, it just swings upwards by 5 mm. Yeah, but that's about it. Okay? So the whole question here, anchors on this point. It anchors on the point of you understanding that it is an inelastic equation, and therefore KE is lost. So you have to accept that KE is lost. So you cannot take the KE of the bullet and convert it to the KE of the entire system here. Okay? Right? You're not supposed to do that. You're supposed to calculate the loss in KE, which is done by this way, using the momentum equation. Okay? Okay, can I continue and do a bit more scenarios? A couple more scenarios? Okay, let me close this. Now, if I want to go through more scenarios, I actually have to go through the last one here, right? Explosions. So let's go through explosions here. Okay. Okay. You can call these explosions slash disintegrations. Disintegrations. Right? Whether this is a type of inelastic, elastic, or perfectly inelastic, right? Whether this kind of interactions is perfectly inelastic or elastic or whatever it is, right? We'll deal with that later, right? But let me show you how to deal with these kind of questions, right? Let me draw a picture for you. You can draw it at the bottom of the page, right? Let's say you have a bullet and a gun like this. Okay, let's say nerf lah. Right? Let's say this is nerf, right? Let's try to keep it less violent, right? Let's say this is a nerf gun, right? Maybe I should draw a nerf bullet then, right? Okay, right? Less violent. Then my question to you is this: what is the initial momentum of this system before you fire the bullet? Zero, right? So once the bullet flies out, what does it mean about the gun? The gun should also have backwards, right? The gun should also have a backwards momentum. How much of the how much would these be? Momentum of the gun versus momentum of the bullet. They will be equal. Why should they be equal? No, no, momentum. You say action reaction, you use Newton's third law. Then when you're talking about forces, I'm asking you why is the momentum the same? No, no. What do you say? What was the initial moment? Why did I ask you that weird question at the? What's the initial momentum at the start? What's the initial momentum at the start, dude? Yeah, the P initial is 0, right? What's the final momentum after the bullet has been fired out? It has to be 0 also. Conservation of momentum of your entire system, including the bullet and the gun. You understand this? So for example, the example that we had just now, the bullet was 10 grams, right? And the bullet was fired out at 300 meters per second. Let me tell you this gun is 1 kg. Let's say the gun is 1 kg. What is the recoil velocity of this gun? I want you to give me the recoil velocity of this gun. Given that the gun is 1 kg, the bullet is 10 grams, and the bullet was fired out at 300 meters per second. What is the recoil velocity? Three meters per second? Negative 3 meters per second, that's fine. All right. So um, you have MA UA plus MBUB equals to 0, and therefore MA VA plus MB VB equals to 0. Right? Mass of the gun is 1 kg. VA is the one that we're trying to find. Right? Plus mass of the bullet is 0.01 times its speed of 300, and this is equals to 0, right? And therefore you can get VA to be 3 meters per second. So the recoil velocity of the gun is 3 meters per second. Ian, okay? Yeah? Okay. So one more time again, why is the momentum forwards and why is the momentum backwards the same? Why is it the same? And yeah, so the total momentum after the disintegration or after the explosion must still be 0, right? So the idea is that the total momentum of the system must be 0. Okay, yeah? Right. So we're gonna do another question here, but this time round it actually so I'm just doing scenarios. Okay, I'm just doing more and more questions. Okay, I'm doing the kinds of questions that you probably will experience in school, right? Okay, so I'm gonna do this now. Can you tell me about the elastic collision again one more time? The elastic collision that I gave you just now, the A and B one. What were the masses? The one that we just did. 10 kg and 2 kg, is it? 10 kg, 2 kg. Is that right? 10 kg, 2 kg. What were the speeds? This is 1 meters per second, and the other one was 8 meters per second. Then after collision was what? So this one is 2 backwards. Hang on, then this one is 2 meters per second backwards. And this is 7 meters per second forwards, is it? Is that right? That was the scenario, right? Ian? Okay, can right? So I'm going to use that same scenario that we did there just now. I'm going to draw a graph for this. Okay, we're gonna draw a graph for this. So again, what kind of collision was this? I specified what kind of collision was this? This elastic, this is elastic collision. So EC, okay, elastic collision. Okay, now we're gonna draw a momentum time graph for these objects. Okay, a momentum time graph for these objects here. So we're gonna draw a momentum time graph for these objects here, right? These two objects. Okay, now PT graph, PT graph. Okay, what's the initial momentum of A? Positive, positive 10, right? So rate for apple, so A. So I'm just going to draw the momentum for A, right? I'm going to put a 10 here, that is this 10. Okay, this for A. What's the initial momentum of B? Minus 16. So I'm going to draw a minus 16, so 10, 20, 10, 20, minus 16, somewhere around here, minus 16, right? Sorry, B blue. Right, because this is a momentum time graph. I want to start drawing this graph. You have to draw the graph. What's the final momentum of A? Okay, never mind, you start drawing first, right? Okay, if you have to, try to use rulers a bit, because or your pencils a bit, just to make sure. I mean, I don't need you to draw it to scale. I just kind of like make sure that the lines are a bit straight. Okay. Okay, what's the final momentum of A? Minus 20. Minus 20. Okay, minus 20, everyone. Minus 20, So the momentum of A will drop from here all the way down. Hang on, let me draw a steeper line, sorry. Okay, I have to extend my axis now to minus 20. And it remains at minus 20 after the collision. So, this is how the momentum of A looks like. From 10 drops all the way down, right, and then maintain at 20. How about B? What's the final momentum of B? Final momentum of B is 14. So notice how I make sure that the collision time is the same for both of them. So final momentum of B will go up to 14. Let's say this is 14. And here, this is 14, for example. Sorry, as I said, use ruler, but I myself don't use ruler then. You understand this? This is how it works, right? So A's momentum is here. This is not velocity time graph. This is a momentum time graph. This is not a velocity time graph. If they wanted you to draw a velocity time graph, they'll tell you, but this is a momentum time graph. I'm asking you to draw a momentum time graph. You okay with this? Yeah, okay, good. So what are some of the features that you need to pay attention to, guys? Very closely, some of the features. Right? Number one, I want you all to draw it big. Instead, if I draw it this big, right, like, hopefully you all draw it big as well. Right? But if you can deal with small pictures, then okay, fine. Number one, you see how the red color line here, right? Isn't this the change in momentum of A? Would you agree that the difference between these two lines here is the change in momentum of A? What is the change in momentum of A? How much? Minus 30, right? Ian, what's the change in momentum of A? Right, so A loses 30, right, units of momentum, right? How much does B gain? Has to be 30, right? Why does it have to be the same? Conservation of momentum of the entire system, right? If A loses 30 units of momentum, B must gain 30 units of momentum, right? You already calculated it out, right? So the changes must be the same. So the next time, right, they could give you a graph question and they ask you sketch the other object. That means if I give you one object only, right, like this, right, without giving you any information, I say sketch the other object. What you need to do is you need to measure the difference in the levels and you give it to the other guy. You understand? So the change in momentum is the same for both of them, right? The change in momentum for this one here, right? And the change in momentum for that one there is the same. Okay, don't need to draw these green arrows. I just want you to know that it's the same, right? So can you all just see it and say it, and agree that it's the same? Can? Good. Hey, there's a lot of features of this graph. There's a lot of features of this graph that I'm going to go through now. Right? I'm going to continue going through. What's the total momentum of this entire system at any time? What's the total momentum of this entire system at any point? Minus 6. Minus 6. Total momentum of this system is minus 6, right? Can you tell me how you got minus 6? What do you do to find the value number 6, minus 6? So you took 14 and you plus it to minus 20. Correct? That's minus 6, right? Then that's this 14 plus minus 20. Right? You get minus 6. This is after the collision. How about before? 10 plus minus 16, you get minus 6. So momentum before and after is conserved, right? But what did I say about momentum? Is momentum conserved during the collision? It is. Momentum is conserved before, after, and even during the collision. Okay? Now it's going to be hard, but here's my guarantee to you that anywhere along this line, right? Anywhere along this line, if at any point in time you take the values and you add it up, right, it always adds up to minus 6. Right? It's very hard to see here now because I didn't draw it to scale. But if you did draw it to scale, you would realize that the momentum, even here or even here, see where they cross? Can you make a good guess what the value is here? Minus 3 each. Right? They cross here, but then they are minus 3 each. So like, you know, where they intersect, that's going to be a minus 3 value here. Right? When they intersect, because the total momentum of the system is supposed to be minus 6 before, after, and even during the collision. Okay, now, and this is the part where it gets really, really strange. Right? The next part is going to get a bit strange for you. So I've been talking about momentum, right? Okay, let's refer to KE now. Let's talk about KE now. Okay, let's talk about KE. All right, question. Is KE conserved before and after the collision? How come you know that? Why is it? Because I already told you it's elastic collision, right? So you expect the KE to be conserved before and after. Okay, so far? Ken? Let me ask you this question, guys. Please pay attention to this. Let's look at this point here, where my finger is. Right, Ian, can you see this point here? Yeah, right, this point here, where the red line crosses the axis, right? Okay, where the red line crosses the axis, okay, can you tell me what's the momentum of object A right here? Is 0, right? At that point is 0. So what's the KE of object A? What's the KE of object A at this point here? 0, right? Why is it 0? Because the momentum is 0. What does this tell you about the velocity? Yeah, so what happens to the KE? So you have to agree with me that the KE here of A is 0. Okay? How about the KE of B? If I wanted you to find the KE of B, how would you find the KE of B? Technically you can find the KE of B, no? Yeah, using momentum, right? You see, what's the momentum of A here again? 0, right? What's the total momentum of the system supposed to be? Minus 6, right? So what does this tell you about the momentum of B at the time when A's momentum is 0? So B's momentum at this very time is 0, right? It's minus 6, right? So the PB equals to minus 6, right? Do you see that, guys? All right. Using this information, can you tell me what's the KE of B? What is the KE of B? Okay, hang on. Let me help you with a shortcut equation. There is a shortcut equation called this. KE equals to P squared over 2M. Right? If you want to find the Ke of an object, you can take its momentum squared divided by 2 times its mass. So what is the what is the Ke of B? What? 9 joules, is it? So while the momentum is 6, then the Ke is 9 joules. Hang on, huh? You all get 9 joules also? No problem. 9 joules. I'm waiting for them. You all get 9 joules also? Okay? Alright. Now my question is this, huh? Do you see that the Ke of A is 0 here? Do you see that the Ke of B is lesser than before? Isn't this supposed to be an elastic collision? What happened to the Ke? Right? So the idea here is, what did I say about elastic collision? What's the definition? Ke is conserved before and after, but not during the collision. Ke is not conserved in this region. It is not conserved in the impact time. Ke is not conserved here. Right? Do you catch all that? Okay, yeah. Now this is only applicable to elastic collision. If it's an inelastic collision, right, the Ke before and after will not be conserved, but the momentum will always be conserved. So do you know how to use this? Like, I'm not done with the analysis yet. I still got a lot more things to analyze. Yeah, still got more things to analyze. All right. Okay. So now let's analyze one more thing. Okay. Which object came to a stop first? A lah, right? Because as time progresses, you see that A comes to a stop first, but B is still moving, right? Then A changes direction, then B will stop. So A stops first. Do they stop at the same time? Huh? I just literally explicitly said that A stops first, then B stops, right? So they don't stop at the same time, right? If you are not given a graph, okay, and I ask you, let's say for example, I give you this scenario only, okay? Let's say you're looking at this scenario, then I ask you, can you predict if both of them will stop at the same time? Can you predict that both of them will stop at the same time? You can predict. Because here's the thing, what happens if they stop at the same time? What does it look like on a graph if they stop at the same time, guys? So they cross zero together, right? Yeah. Okay, what's the total momentum of the system if they cross zero together at the same time? Then the entire momentum must be zero, right? So you look at the initial momentum of this system. What's the initial momentum of the system? Is it zero? It's not zero. How much is it? It's minus 6, right? So since the initial total momentum is not zero, they will not cross at the same time and they won't come to stop at the same time. Right? So during collision, the objects will stop one after another. And in fact, if you draw it out, you realize that A stops first, then B. As in, they are not moving at the same time. If you draw the graph of momentum time for the gun and bullet, right, both of them are zero, then they split. So that's not a collision, that's an explosion, that's a disintegration. Are we all clear on this? These are the questions that they will ask you in your exams. Why are you not writing it down? Because next week I ask you, then you'll be like, I cannot remember. Then next week I'm doing something else already. Life moves on. Right? Don't get left behind. Okay, as impossible as it sounds, A here, bigger, B here, smaller, right? A and B going towards each other, okay? In a slow motion, so when they collide, right? A is the one that stops first, right? A is the one that stops first, and then it U-turns backwards, right? But B continues moving forward a bit before it U-turns. So this down here, right? It's a very small period of time, but A stops and turns backwards first, because once you go from positive to negative means that A will then bounce back already. B goes from negative to positive means B will bounce back. But it's a very short period of time where what happens is that A will bounce backwards first, B moves forward a little bit, then B moves backwards, like this. Yeah. Okay. So from this black marking here to this black marking here, they are always in contact. So okay, I can't make this any bigger, but this is what happens. So they will collide, they will compress, right? So A starts to move backwards, but B moves forward a bit. Then they start to move backwards, then B will bounce off. Imagine you running into an inflatable castle, those inflatable balloons, right? You run into it, then you make a dent, right? Then the castle moves back a bit, then you move back a bit. So it's like there's a very small, slight, minute movement where where this A ball moves backwards first, right? Moves behind, but this B ball is still moving in front a bit. Then they rebound like this, right? Yeah, the short period of time is when A starts to U-turn backwards first, but B is still inching forward a little bit. But it's a very short amount of time, even shorter than the entire contact time. Yeah. So it's just like there's like a delay, like a little bit of lag for B. Okay, but you don't worry. This is not how it happens. Okay, can not done yet. One more thing to analyze. One more thing to analyze. Okay, how do you find the force that each object experiences? How do you find the force that each object experiences? That's just a question. How do you find the force that the objects experience? Before collision, does the object experience any force? So when does it experience a force? During the collision, how do you find the force from this graph, right? From this graph for the objects? That means what am I trying to find here? Gradient. Why would you say area? Gradient. The gradient of this graph will give you the force that the objects experience. Right? The gradient will give you the force, right, that the objects experience. In fact, you can even take this small gradient here. It doesn't even need to take the whole thing. But the gradient, right, equals to force experience.
This is force on one object.
Huh?
This is the force on one.
Guess what? It's the same force for the other object. They have the same gradient. Just one is positive, one is negative. Why do they have the same gradient? Huh? When they collide, dude. When they collide, when in the middle of collision, when they're in contact, A and B, right? B experiences force, A experiences a force. This this is one force on A, this is one force on B. Why would you say times two? There's no times two. I'm just trying to find a force. But my question to you is, why are the forces the same? Why is this F the same as that F? They are action reaction pairs. So the gradients of these two graphs will definitely be the same amount of gradient, but one is positive, one is negative. I'm not taking down enough notes. Okay. What if I tell you that your test, your upcoming test, this question is going to come out? Like legit, this exact same question is gonna come out. If let's say I drop a note to Lokam, then I ask him to set this exact same question, what are you gonna do? So you go in there and swing it, lah. Huh? Go in and do it. Okay, and then I hope you get it right. Okay. Right. So this is how you use how you analyze this graph, right, all the way to the end. Last question though. If I only simply give you the graph like this, okay, without any idea what the masses are you able to tell whether this is an elastic or inelastic collision? Yeah, you won't be able to tell. Right? You can't tell whether this is elastic or inelastic. Right? Because for inelastic or elastic, momentum is always conserved, right? So even though the graph shows you that momentum is conserved, right? You don't know the mass, you don't know the velocity, you don't know the situation, you have no idea whether this is an elastic or inelastic collision. So no, you can't. Right? Unless they tell you the masses, then maybe you can back calculate the KE here, and you can find out the KE there. Right? If the KE of the initial and the KE of the final is the same, then yeah, this is elastic. Otherwise, if just the graph alone not good enough, you can't tell. Okay? Right, so this is how you convert the collision into a graph and how you analyze the graph, right? If you are given a graph, right, I think I'm more than happy that to tell you that they've given you a lot of information. If they give you the graph, right, that means you can derive a lot of things from this entire thing. You can go and find out the total momentum. You can find out which one stops first. You can find out what's the initial final momentums, all that, everything, right? If they give you values like this only, oh, then that's tough. That's even tougher than giving you the graph. Giving you the graph tells you a lot of information. Okay, Ken, that's it for the graph, right? That's it for momentum. That's it for momentum. Okay. I'm going to jump into work energy power now. Right. If you need to take a toilet break, go ahead. Take a toilet break. I will start to open the work energy power stuff. But it's in the same set of notes. Ian, you have it, right? Hello, Ian. Oh no, already? Hang on. It's here. This one here, the one with the car one. Work energy power. Don't have? Have? Don't have. Don't have. So I send you to soft copy. You also taking soft copy? Oh, you got iPad now? Okay. I will paste this into the shared drive. Sorry, it's there. Right, so you go into the shared drive, you should be able to find it there. And then you go towards the work energy power side. You have it, right? Okay. Then for the two of you, do you have the printout for this one? Don't have 34 print to 38. Sorry. Thank you.
They say if I don't go right, I have to pay a fine of 10,000.
What?
So, Navy diving.
NDU?
Ah,
Why?
call me up for or
Or
Do you even like doing it or not?
no, they can don't do it.
Yeah, can they can. Yeah, just reject
But no,
I think I prefer to see more Garang one becoming NDU lah. Oh, NDU the two of you. Don't just be storeman NDU, naval diving unit. Your swimmers right? You all will sure be picked for NDU one. Yeah lah, don't just be storeman can already. Just go through life becoming storeman, becoming clerk can already. Don't worry about achieving anything. Right? Just keep low profile. Walao, you go high profile, what will happen? Walao, they ask you to do a lot of things, man. Wow, do this, do that. Of course, they'll pay you damn a lot of money lah. But do you want the kind of money? Do you need the kind of money? No need, right? Don't bother. Just be storeman and clerk. It's okay, and just lay low profile, right? Resume. When it comes to resume, when you're applying for jobs, what were you in army? Storeman. Okay, never mind. Just go. Just just move on. Next interview, please. Right, like that. Don't worry, just lay low. Right. It's called demotivational speech here, dude.
legit one.
Yeah, like what would you want?
Now become police.
Infantry
Not yet.
Yeah lah, correct lah. Storeman lah.
Now become police.
To do what?
Dulu.
You don't know Have you dragged the dead body before?
But police more fun. Yeah.
Do you know how many slashing cases happen in Singapore? You want to go into police?
Oh, yeah.
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 I've got friends in police, what? A lot of friends in police. Right? They tell me the same thing. The worst cases are the slashing cases. We see blood everywhere. That's police life, oh. Hey, what do you want to do? Man comms Just sit there, man comms all the time. Man comms.
That one injury though.
Huh? Then you have to prove that you got injury. Stop swimming
Oh.
Then if you continue swimming, the next thing they'll do is ask you to go for NDU already, what? Huh?
Quit swimming, then they
Quit swimming, yeah, just quit. Quit swimming, right? Then after that, just take all the low profile stuff, all your like as low profile as possible. Just go for the lowest profile one, right?
if your eye,
Come on, man. This is not a this
if it's good, then will they go for?
you can reject, yeah, whatever good things that people offer you, you just reject. How about that? Right? Do you think you sure you want to live your life like that?
No.
No lah, then what? If they offer you, take lah.
That's one thing.
You know what? You okay? So the question, so the thing is that at some point in life, right, you realize that opportunities keep passing you by. You know, how come people don't offer you this anymore? How come people don't offer you that anymore? Like, people just kind of like, okay lah, let's go and look for someone who was a bit more potential one, and then give them the job, give them the pay, give them the money, give them the bonus. Dude, that's gonna happen if you keep letting opportunities pass by you. No, then what you want to do?
It is normal.
What's normal? Normal infantry lah. Then you go run lor.
SE.
Run lah, run. Come on, guys. All right. You know what they say in football? Man up.
Oh.
Time to man up. Right or not, Ian? Man up, right?
Hey, that time damn funny, but the football match, then Ian let me angry at the referee.
Oh no, Ian. Were you angry at the referee?
He scolded the referee. Yeah. Are you ref?
Are you ref? And who else is in football? I got one guy in football now. Jaden. Not this one. Jadon. Yeah, Jaden. That's right. He's year 6, right? Yeah, year 6, older than you. Yeah, I think so, yeah. I don't know which Jaden the Jadon. I don't know what's the yeah. No, he seemed quite normal. I mean, you mean you got 2 Jadens in football? Oh, okay. Man, how many Jadens do you have, man? Sorry, man, but seriously, there's a lot of Jadens around. Why? Okay, guys, listen up. We're going to start on work energy power. We're just trying to finish this within this lesson here. All right. If you miss it, you miss it. Right. Next week, I'm moving on to circular motion. I'll be handing you all homework after today. Still manning comms, man comms all the time. Things happen already. It's still manning comms. You're manning the wrong side of comms. Man this comms. Right. Eyesight is also a form of communication. Man this comms. What's the work done by this force? What's the work done by the force? 120 joules. Agree? Okay, good. Same box, same force, same distance. This time around, friction is 5 newtons. Okay? Friction is 5 newtons. What's the work done by the force? What's the work done by the force? Okay? Still 120 joules. Right? Why? Why is it the same? Because of the question, what's the work done by the force? The force is 15. The force pulled this object for 8 meters. Whether or not there's a friction, right? It doesn't change the work done by the force. Who's the one who is applying the force? Who is applying the force? Is the force originating from the box itself? Did the box give itself its own force? No, right? So who's applying it? External source. Some dude is pulling it, for example, maybe, right? Let's say this guy is pulling it like that, and he pulls it for 8 meters. The work done by this man is 120 joules. If there's friction for the first 8 meters, the work done by this man is still 120 joules. So the work done by the force does not affected by the friction. So what's the difference then? What's the difference? In terms of energy, I want you to, since we are doing work energy power, everything in this chapter must be discussed based on energy now. So what happens to the work? Okay, first picture, what happens to the work done by the man? What is it converted into? Kinetic energy, right? Work done is what? What is work done? Work done is energy. Force times distance is this energy, right? So work done, right, by this man, he's converting his chemical potential energy into the kinetic energy of the box. Right? Work done. Work done is converting energy into kinetic energy. Did I say speed? Did I say velocity? Did I say acceleration? What did I say? KE. You understand this? Right? So how about for this box then? What is the work done being converted into? Work done by the man. Let's say the man is pulling again. What's the work done being converted into? The work done is being converted into, a bit of it is converted into KE, and another bit of it is converted into heat and sound. Work done against friction. Some of the work that he does is used to overcome friction, is to do work against friction. Learn the phrase, do work against friction. Work done against friction. At the end of 8 meters, what is the KE of this box? At the end of 8 meters, at this end of the 8 meters, what is the KE of this box? At the end of these 8 meters, once this box has been pulled for 8 meters, what is the KE of that box? This box on top. What's the KE of this box at the end of these 8 meters? 120 joules. The work done is 120 joules, so the box will gain 120 joules of KE. The man will lose 120 joules of chemical potential energy. Do you understand this? So when the box is here, the KE of this box is 120 joules. What's the speed of the box? Can you find the speed? How? What will be the speed of the box? I need the mass of the box. Let's say the mass of the box is 5 kg. Can you tell me what's the speed of the box then? What's the speed of the box? Half mv squared equals to 120. So v equals to, on the dot, 6.92 meters per second. Can you all get the same values? You all can? Good. Because here's the thing. What method have you used to find the final speed of this box? The energy method. You've converted work done into KE. You use KE to find the speed of the box. Can you use another method to find the speed of the box? What's another method? You'll be using the force method. So if this is the pulling force acting on a box, 15 newtons, and there's no friction, what's the resultant force on this box? It's 15, right? So if there's resultant force, there must be, how much is the acceleration of this box? 3. 15 divided by 5 kg, right? 3 meters per second. 3 meters per second for 8 meters. Think of an equation to give me the final speed of the box here. I'm testing you on your kinematics. Because you have a test in week 5, right? So what is the speed of the box? I'm just asking you to validate that it is 6.92 meters per second. B squared equals U squared plus 2AS. 2AS, do you get the same answer? Okay, so you can use V squared equals U squared plus 2AS. Right? What I'm trying to show you here is that you can use the force method, right? You can calculate the speed and the distance. If you use the energy method, you can also calculate the speed, right? Using the energy. Right? I'm showing you 2 ways, right? So topic 2, at the end of topic 2, once you start learning work energy power, you can start to accumulate all the methods that you've used to go and find the values that they want, right? But let me tell you something, okay? Using the energy method is always a better idea. In most of your kinematics questions, or sorry, your most of your mechanics questions in topic 2, using the energy method is always a better idea. Okay, good. So how about the one here at the bottom? Right, how much KE does the object have at the end of 8 meters? Right. So the KE here will be, what will be the object or the KE of the box after the 8 meters? What's the KE of the box? Come on. 80 joules. You all get 80 joules? 80 joules. What's the work done against friction? I want the work done against friction. How much was the work done against friction? You say 40 joules, but how do you get the 40 joules? So basically 120 minus 80, you get 40 joules. Any other method of calculating this? 5 times 8, friction times distance, 5 times 8, 40 joules. You write that down? Ian, have you copied down everything? Okay, good. Right, so this is the concept of work done. This is a very important concept, right? So this all these small little things here, right, sets the language for the whole thing that you'll be doing, right, for this part of this chapter, right? This sets a language, huh? Can I continue on? Can I do another scenario? Why are you doing your things all over? I don't understand. No. Seriously. You see me when I start on a blank piece of paper like this, you should also get ready already. Ready? Okay. Next one, huh? Next scenario. All right, this is the next scenario here. I have a box, 2 kg, right? It was moving at a speed of 4 meters per second at first. Later on, the speed of the box, right, was same box, huh? Right. So it has now the box is 10 meters per second. Okay, the speed of the box initially was 4 meters per second, and then the speed of the box was 10 meters per second. All right. So now the question is this: what was the work done on the box? What's the work done on the box? Hmm? 24 joules? 84 joules? All right. So the important thing I want you to learn here is this, huh? Right? Okay, I'm going to write down something. Don't write this down. I'm going to show you this to you, huh? So some students will do this. Half m del v squared. Okay, some students will do this, right? Then what do? They will say something that is half m 6 squared, because 10 minus 4, right? So they might do this, 10 minus 4 squared, like this, right? Don't write this down, because I want you to see this and I want you to remember this, that this is completely wrong. You do not take the difference in the speed, then you half mv squared that speed, and then say that that's a change in ke. That is completely wrong. To find the change in ke, right, the correct way of doing it, you should, and let this burn this in your memory, huh? Half mv squared minus half mu squared. You must always do this, right? So you take half m v minus u, sorry, v squared minus u squared, like that. And you should realize that this is not the same as v minus u whole thing squared, right? It's v squared minus u squared. Okay, so then you take half times 2 times 10 squared minus 4 squared, right? And your answer is, what's that again? 84. 84 joules. The work done is 84 joules. Okay on this? Yeah. So even though you don't have force times distance, right, you are also expected to find the work done, right, by finding the difference in KE. We good? Can? Let's move on. Next scenario. Okay. So obviously in the data booklet, you do see this equation. All right. They tell you the work done is equal to Fs cosine theta. Fs cosine theta. Right? You see that equation, right? Fs cosine theta. Do you know why the equation is written like that? Fs cosine theta. Can I ask you to look at this thing and tell me why? I have to resolve f, right? I have to resolve f, and when I resolve f, what do I see? I will get the f sine theta on top and the f cosine theta at the bottom. Which component does the work? F cosine theta. And that's why the equation fs cosine theta, because it's essentially f cosine theta times s. Are we clear on this? And this is why you have to resolve it. So what does the f sine theta do? What does the f sine theta do? You have to declare that this component f sine theta does no work. The work done by the f sine theta is 0. That means a force is applied, but the object did not move in that direction, so the work done is 0. Okay? If you apply a force and the object doesn't move, what's the work done? 0. If you have someone holding a book like this, okay, right? What is the force that the person applies on the book? Right? So the force applied is this one, right? The normal contact force. If the person walks to the right, what's the work done on the book? 0. Why? Because the force and the direction of movement is not the same. So if you only take the component of force in the same direction as the motion, you take that component multiplied by the distance, you get the work done. Okay so far? Right. What's the trap for this equation? If I'm setting an exam, I will definitely try to trap you by giving you a diagram that looks like this. And I would like to see you use f cosine theta blindly. Yeah, f cosine theta is going up. If you just blindly use f cosine theta, you're going to get this completely wrong. So what I'm trying to tell you is that in all situations, always look at where the angle is given to first. You see, right? The equation in the data booklet gives you like this. Work done is fs cosine theta. That's because this theta was defined as the angle from the horizontal. But if I give you the angle from the vertical, you have to change the equation altogether. Right? So don't just blindly, oh, this one easy, I see the degree like that, I just use the equation like this. Gone case, you do smart. Why? Not because you don't know, because you're lazy. You never check. You just assumed. Right? So work done in this case is f sine theta times s. So the data booklet equation is not a consistent thing. Right? The data booklet equation is not always correct. Sometimes you have to flip the equation around, right? Or to use the. So what's the deal here? The deal here is just remember to use the correct component, right? Just remember to use the correct component. If you see the component, the object is moving towards the right, the displacement is here, then you have to use the f sine theta times s. Right? I'll tell you this, okay? At some point, all your classmates will all be able to understand this. Right? At the very end, whether or not you make it on your test or whether you do well on your test really depends on whether you're careful enough. Right? If you're just like, I look at equation, I apply, right? Because one of my seniors say, oh, you just need to look at equation and apply. I just look at equation, I apply, right? And you get it wrong. Then you ask, go and ask your senior why. Why do you get it wrong? Right? Right. So be very careful whenever you're doing the questions. Right. So that's work energy power. The first part, the force times distance. Okay. Right. We've also covered this one here also. There's the work done in springs, but before I get there, there's one more thing I need to cover. Right. The springs one, I'll leave it alone first. Right. I'll do the springs one later. I want you to do this. Work done. Right. Manipulation. Piece of paper. Work done. Work done is force times distance over time. Sorry. Work done is force times distance. Force times distance. And this is equals to sorry, no, yeah, I got this wrong. I'm talking about power here. Yeah, power. And power is energy over time, right? So energy is work done over time, right? So it's force times distance over time, and this is force times distance over time, and therefore power is equals to force times velocity, right? Okay, scenario. I'll give you a car, right? The maximum speed right now is 30 meters per second. Okay, the Vmax of this car is 30 meters per second. The driving force of the car is 5,000 newtons, right? So you have a car, driving force is 5,000 newtons, Vmax is 30 meters per second, right? Simple question, what is the power of the car? Right, it's just force times velocity, right? So this one times 30, so you get 150,000 watts. Okay, this one's easy. But now I'm going to throw you another question regarding this car also. How much resistive force is the car experiencing? How much resistive force is the car experiencing? Zero resistive force? If it's zero resistive force, that means if there's no resistive force, then this is the resultant force. If this is the resultant force, you are not at maximum speed. You will continue to accelerate. So here's a clue, right? And I will also again set papers just to trick students by using the word Vmax. Maximum V actually means constant speed, right? Maximum speed is a type of constant speed. It is constant. It's maximum, but it is constant. But because it is constant, how can the car be at constant speed? It's basically terminal velocity, right? So the idea is terminal velocity, but how? In terms of forces, how is the car at constant speed? How is it at terminal velocity? So how much is the air resistance? How much is the resistive force? 5,000 newtons. So the power of the car, right, is used to merely overcome the resistive force of 5,000. Because I did tell you that it's a constant speed. Are we okay here? Can, huh? All right. Further question on this, right? We go in deeper and deeper, right? What is the overall energy conversion of this car? I want the overall energy conversion of this car. What's converting to what? Overall, from the start and the end, I just want to know what's the starting energy to the last energy. What's the overall conversion? So what does the car burn? Chemical potential energy. Okay? Right? And what is it being converted to overall? Overall, heat and sound. Not KE. Right? Why is it not KE? Why is chemical potential energy not being converted into KE? Because if chemical potential energy is being converted into KE, then the car will gain KE. So what's happening to the car here? Is the car gaining KE? No, right? The KE, there is KE. There is KE, but the KE is constant. So when it's already at this maximum speed, the chemical potential energy, the fuel that's being burnt in the engine, is merely to overcome the resistive force and therefore converted into heat and sound directly. Chemical potential energy converted to heat and sound, right? It is not converted into KE. You can say, how about in the middle? Yes, chemical potential energy is converted to KE, but ultimately, one for one, chemical and potential energy into heat and sound, right? This is because it's a constant speed, right? Again, it's because it's constant speed. Cannot. Okay, huh? What is the rate of heat and sound being produced by this car? What is the rate of heat and sound being produced by this car? Rate of heat and sound being produced by this car. It is 150 watts, 150,000 watts. Because the power of the car, it means the car is burning 150 joules every second, right? Okay, if you never hear me say this before, so I want you all to learn this. Every time you see 150 watts, every time you see the units watts, the first thing you think about is joules per second. So 150,000 watts is 150,000 joules every second. So this is the amount of heat and sound is also being produced by this car every second. I know it sounds excessive, but this is the true amount that's being produced. Right? So this is power. Right? We talked about work energy power, this is power. Does anybody have like questions that you sent me recently regarding some of these topic 2 questions that I've not been like, I said that to wait until I finish, then I go through with you. Did anybody send me? Did you send me? Somehow I think you sent me some work energy power thing. Can you arrow up the thing? Or can you send it to the group? Okay. This one here, I will now use this example that Glendon sent. Yeah, as the sample question for the next part that I want to teach. So I've taught you power, right? Okay, what's the one energy equation that I've not taught you yet? Right, GPE lah. GP equals what? MGH, huh? Right, just MGH, right? GP equals MGH. Can? Right, and I'm gonna use the this whatchamacallit, this this equation, this question that Glenda just sent to the group. Right, I'm going to use that as an example. Can you all see the question? For those using the iPads, you can just copy and paste the thing onto your iPads, and then we're going to start solving the question also, because that question is for MGH. Yeah, I'm going through MGH now. Copy and paste ready? Okay. So we have a airplane here. Let's draw an airplane. Then let's draw the ground here like this. Let's draw the dude falling out of the plane. Okay. Miraculous, you fall 370 meters. But you land in the snow, so not so bad. Okay. So based on the story given, which is absolutely not any of our business, but the path of this pilot as he falls out of the plane, the path of his motion will look like this. Is this projectile motion? Nope. Absolutely not projectile motion. Why is it not projectile motion? Why does this curve not show you projectile motion? If I draw a curve for you and I show you that this is the path, you have to tell me why is it not projectile motion. No, but based on the curve, you have to look at the curve and tell me why this curve does not show you projectile motion. No, what nonsense. Projectile motion nothing to do with force. Come on. I mean, the plane was flying straight, and when he jumped out, right, he was flying straight at first, right? But of course, because of gravity, so he starts to fall down, right? If the plane had an initial velocity of, I don't know, maybe 50 meters per second, right, I can also guarantee that he's also going to have the initial velocity of 50 meters per second. But that's not the point. The point is this: I'm not going to give you a value, right? I'm just going to ask you this, right? It's because the values might be a bit confusing. Given that a path drawn like this, right, explain why this shows that this is not projectile motion. Huh? It's not parabola. Not good enough, but not bad. The line at bottom too straight. You put opinions to it. Too straight. He's not wrong. I think he got an idea. He's not wrong, but give it a more physics way of explaining it. The line at the end is, yeah, is vertical, no? The line is vertical, right? The motion, the path of his, like his path is vertical, right? What does that mean? If the path is vertical, stop saying falsely. It's quite scary, right? That you have to get all the terminologies correct within a few lessons, right? But that's what you need to do, right? You need to unlearn all the bad habits that you learned from secondary school. Okay, but yes, the path at the end here indicates that the horizontal velocity is. When you have a vertical motion, what is your horizontal velocity? It's zero, right? The horizontal velocity is zero, right? The horizontal velocity is zero. Right? Good. So why is that not projectile motion? Good. Right? For projectile motion, the one of the components of the velocity must be constant, right? Constant velocity in one direction, constant acceleration in perpendicular direction, not other direction. Yeah, perpendicular direction. Other direction will indicate this direction and then the other direction. That's wrong. It must be this direction and the perpendicular direction, right? So by drawing a path like this for you, right, you can guarantee that there's no projectile motion here because the horizontal velocity is not constant, right? Because projectile motion is supposed to be defined as Constant velocity in one direction, constant acceleration in the perpendicular direction. You get this? Anyway, that's not the point of this question. The point of this question is I'm drawing this for you. Okay? I'm just drawing it for you because they said terminal velocity was 35 meters per second. So if you see the words there and then they say 35 meters per second, can I assume that it will be 35 meters per second here when the line is about quite straight already? Can I assume that's 35 meters per second? Can, right? Can I assume that this part is also 35 meters per second? Can I assume that this is 35 also? Can I assume it's 35? Why is it 35 all the way? Because that's what terminal velocity is. Right? That's what terminal velocity is. You understand? Okay, not? Okay. So basically, this man will approach the floor, the snow, at 35 meters per second downwards. It means just before he hits the snow, his speed is 35 meters per second. Okay? All right. Then the next thing is he will be embedded into the snow. How deep? 1.1 meters deep. Okay? First question, what is the work done by the snow to get him to stop inside the snow? Like that, at a crater. Like this. It means he's embedded inside here like that. What is the work done by the snow? How would you calculate work done in this sense then? Force and distance. Right? That's what we just learned, right? What's a big problem? Look at part 2. Look at the question 2. Part B. Look at part B. Part B asks you for the force. So if you don't have the force in part A, and you're supposed to find the force in part B, then you cannot use force and distance in part A because you don't know what the force is yet. Then how? You have to consider the change in energies. Okay? Right? So in order to get this guy to stop inside this snow, right? What are the energies that needs to be converted for this guy? Like what are the energies that needs to be converted into heat and sound? KE needs to be converted into heat and sound, right? Okay? Right? Then you have to convert KE. You have to calculate the amount of KE because what's the final KE here? Okay, hang on. Is that the only energy that you convert? What else? How much GPA? So this part here is the part where a lot of students will miss out. They will miss out this 1.1 meters, right? So you have to realize that in order to stop him, his KE here and the GPE here must be reduced to 0 here. So it's KE plus GPE equals the work done by the snow. Ian, are you there? Copying still? Right? KE plus GPE equals the work done by snow. Then you can work this out already. What? Calculate it out. So how much is the KE plus GPE? Because that's the work done by the snow. 469 or 46,933 joules. Is that right? Yeah, I think so. It's 35, right? Why is the answer key like that? Huh? No, you just, so energy, right? You just keep everything positive. Yeah, don't worry about the answer key there. Oh, you have to keep everything positive, so that's not the correct answer. So what's the answer you got? What? 48616 joules. Okay? 48616 joules. Okay. But you look at the answer key, it says that the answer is negative. Right? Basically, it's saying that the answer should be negative for 48,616 joules. Right? Why? So this is the first time you're learning this. Work done can be negative also. Right? Okay, but does this mean that work done is a vector? If you got positive, you got negative, does it mean that it's a vector? Absolutely not. Work done is still energy. Energy is not a vector. Right? So why is it negative though? Negative means loss of energy. Read the question again. What's the work done by the snow to bring him to rest? So the snow causes the man to lose this amount of energy. So the work done by the snow is this value here, negative 48,616 joules. Okay? That's what work done. That's why work done is negative. Right? So if you get a question like this again, what's the work done by the snow? Then the answer is truly negative. If I change the question and ask you, how much energy did he lose? How much energy did the man lose? Then your answer will be this value in positive value. Okay on this? What's the work done by the snow? Force and distance, right? So how much force did the snow act on the man? This is the part B question. This is the force by the snow. Right, this is the force by the snow. 44,196 newtons. Right, you have to round off, huh? Right, so you have to round this off to 44,000 newtons. Right, 2SF. Right, same thing for the one above also. You have to round it off to 1SF, 2SF, so it's 49,000 joules. Are we okay so far, guys? Oh, okay. So to be honest, I don't like this kind of questions. I don't like when the teachers are trying to catch the students on negative signs. Let's say for example you put 48616 joules, right? Then they mark you wrong. Then they say that you're wrong because suppose we have negative sign. Right? When teachers do that, I absolutely deter that kind of behavior. Right? So how do you safeguard yourself? I think that's a more important question. How do you safeguard yourself against this kind of teachers where they will take away marks just because you forgot to put a negative sign? Right? You can do this. You can say that work done by snow. You put a statement. You calculate already, right? Then you put a statement. The statement will be the one that covers you. Work done by snow, right? Causes man to lose 49,000 joules of energy. Right? And then here's the thing. If they still want to find fault and minus marks away from you here, right? I'll tell you this. I guarantee you that IB doesn't care. Right? I guarantee you that IB doesn't care. The final answer is 49,000 joules. Is 49,000 joules. You write down 49,000 joules, IB will not care. Because IB knows that you all understand. It's only this kind of questions, right? Okay, if the teachers want to mark students down on these kind of things, right? The first instinct I have is that the teacher was an A-level teacher at first, then he converted into IB teacher, and therefore he's still taking all his archaic, right, mentality from the A-level side, thinking that, oh, it must be negative, I must see the negative, then I'll give the marks. That doesn't work in modern days, right? So what do you do to protect yourself? You write a statement down. If you write a statement down like this, right, he'll get stuck. He'll be like, I can't take away marks from you because this is true, right? So I will always say leave a statement, right, and then they won't be able to mark you down on this. Can? Right. So that's the first two questions done. The third part, what's the work done by air resistance as he fell? Okay, what's the work done by air resistance as he fell? Part C. Can we do part C now? So we're done with A and B, yeah? So now we do part C. Do you see part C? Okay. Now part C, right? If you read the question, do you realize that they want you to make one assumption? Actually, I'm very perturbed by the last one. Okay, but never mind. So part C, right? They want you to assume that he was already at terminal velocity all the way. That's what part C wants you to do. You look at part C. They want you to imagine that immediately after you jump out of the plane, right, you hit terminal velocity all the way already, right? Because it says terminal velocity is 35 meters per second. Then they want you to find the work done by the air resistance as it fell. How do you find that? For the last one, what you do is this: you find the GP that he would have gotten first when he's falling in air. When he was falling this, right, how much GP would he have have lost? So it will be mg times 370. Okay, mg times 370. How much is that? $283,117 joules. That's the amount of GP that he would have had, right? Which also means that without air resistance, right, the amount of GP that he has so do we assume that, okay, what? Oh, wait, actually there's another way, right? You can take air resistance times distance, right? That means you don't need to do the GP lah. You don't need to do this GP. You take the air resistance. So, but this is assuming that he gets air resistance of how much? 78 times 9.81, right? 78 times 9.81. That means he gets a air resistance of 765.18 newtons immediately after he jumps out. Up there. And then you take this, you times 370 meters, right? Oh, which is the exact same number. Hang on. Huh? Same equation, right? So am I right to say that they want to think that the air resistance acts immediately or not? It's not right lah. I don't think it's right to imagine that the air resistance acts immediately all the way. I still think that it should be like that. I still think that it should be like this. Yeah. So I think the best thing is this. This is the amount of GP, right? You can calculate what's the final KE. Again, what's the final KE? Half m v squared. 47,775 joules. Right, that's the final KE, right? Okay, then the work then that means I was right in the first place. That means you go and find out what's the total amount of GPE loss when he fell down, right? All of this is supposed to be converted into KE, right? But his final KE is only 47,775. Okay, so you find the difference, the GPE minus this KE, right? That would be the work done lost to air resistance. Right, so the energy loss to air resistance is equal to 283,117 minus 47,775. 235,342 joules. Here's the energy loss to air resistance. Ian, you okay there? Then, any issues? Make sense? Logic? GPE loss here, final KE there, so the energy loss to air resistance is the difference between these two. Okay, huh? Yeah, that's it for part A, B, and C. Where's this question from? The assignments, is it? The worksheet. Do you do this? Yes. This is topic 2. Continue to do the topic 2 one, huh? Yeah? Again, it's the same nonsense as just now, lor. What's the work done? So how do I protect myself? I say energy loss due to air resistance is this amount. I can't put a negative sign to this thing here, so I put a statement again, right? Energy loss. But let me tell you, your teachers will try to catch you on this one, it's been 2 hours already, I guess. Any more questions from schoolwork? You have to start doing though. Yeah, the topic 2 schoolwork. Yeah. The teacher went through all the questions already. Then this one didn't go through. Okay, I think you're missing. Okay, bye. You know where the questions are coming from, Jeremy? Okay, can. These are so you got these two kinds of equations, these two kinds of worksheets, topical and mark worksheets. The ones that you're going through in school. Hey, Ian, see you. Bye bye.